Hello students, today we are going to discuss about thermodynamic state variables. We have already discussed about state variables. The state variables are nothing but the variables which are needed to describe the state of a system. Here system is nothing but an object under observation is called as the system. Here we are discussing about ideal gases. Any ideal gas, every equilibrium state. See here, every equilibrium state, every equilibrium state of a thermodynamic system, is completely described by specific variables. Such variables are called as thermodynamic variables. So here the thermodynamic variables are, for example, pressure. Pressure is needed to describe the state of a system. Volume also needed to describe the state of a system. And temperature, pressure, volume, temperature, and amount of substance, etc. are the thermodynamic variables. Amount of substance are thermodynamic variables here. Okay, see here, the important thing here is every equilibrium state. Every equilibrium state of a thermodynamic system is completely described by what? Some specific variables. So here we can able to measure pressure or volume or temperature only when the system is at equilibrium. If the system is not going through non-equilibrium state, we cannot able to find out the exact pressure of the system or exact volume of the system or exact temperature of the system. Okay, for this I am for example, I am going to explain one thing here. See, I am taking a system like this. and this system has two partitions. Like this. See here, consider this is nothing but vacuum. This side is a vacuum only, and this side some gas molecules are there on another side. And consider here the gas molecules are like this on one part of the portion, and in another part there is no gas molecules here. Here it is nothing but vacuum. Okay, when we remove the piston in between them, consider this is a piston. Okay, when we remove it, suddenly the gas will expand. This is called as the sudden expansion of the gas. So this is almost abrupt process, almost spontaneous process. When you remove the piston in between the two portions, the gas this side will be expanded into the vacuum. So this is sudden expansion. We cannot able to measure pressure, volume, temperature, and amount of substance of this system, as this is not going through equilibrium state. So here in this example, system is going through non-equilibrium states. So in this case, we cannot able to measure the thermodynamic variables such as pressure, volume, temperature, and amount of substance, and etc. So state variables are defined as a thermodynamic system which is needed to a system is completely described by some specific variables when the system is at thermal equilibrium and mechanical equilibrium. So when the system is in equilibrium state, the variables that are needed to describe the thermodynamic system are called as the thermodynamic variables, state variables. Those variables represent the state of a system. So we call them as state variables here. So here another example is, suppose a system has large number of chemical compositions. Chemical compositions. Consider when this explodes into small fragments. When this explodes into small fragments, when this explodes, this is also a sudden expansion. It is also going through non-equilibrium states. It is also going through non-equilibrium states. So we cannot measure pressure, volume and temperature, etc. So here, when the system is going through equilibrium state, when systems are going through equilibrium states, we can measure thermodynamic variables, thermodynamic state variables. In first example, when the gas is expanding freely against the vacuum, after some time the system attains some equilibrium. That is, it attains both thermal equilibrium as well as mechanical equilibrium. So when this gas molecules expanded into the another side, that is into the vacuum, after some time this total system attains, this system attains both thermal equilibrium. Thermal equilibrium is nothing but on both sides the temperature is constant. The temperatures are equal. So temperature is constant and it attains both thermal equilibrium and mechanical equilibrium. We know mechanical equilibrium is nothing but in which the pressure remains constant. Pressure is equal to constant. So it attains both thermal equilibrium as well as mechanical equilibrium. When it attains thermal and mechanical equilibrium, we can able to measure thermodynamic variables such as pressure, volume and temperature and amount of substance in this case. So in short, the thermodynamic state variables describe equilibrium state of a system. Now the various state variables are not necessarily independent here. The connection between, so here the connection between state variables is called equation of state. So here for an ideal gas is nothing but what? A gas which has no intermolecular attractions. That means potential energy term equal to 0 in internal energy. So the internal energy is purely depends only on kinetic energy. Kinetic energy depends on what? Temperature. We know this relation already. We have discussed about it. So for an ideal gas, the relation between thermodynamic variables are PV is equal to mu RT. PV equal to mu RT. So here P is nothing but pressure of the gas, and V is nothing but volume of the gas, and T is absolute temperature of the gas at equilibrium state, and mu is nothing but amount of substance in moles, that is number of moles, amount of substance, and R is nothing but universal gas constant. Universal gas constant, and its value is given by R is equal to 8.314 joules per mole per Kelvin. This is the value of R value in equation of state, thermodynamic equation of state. So now we are going to discuss about the state variables are two types. Those are intensive and extensive properties. Now I am going to discuss about intensive and extensive properties, or intensive and extensive variables. Okay, the definition of intensive variables is nothing but when we divide the system into large number of partitions. That is nothing but when we divide the given thermodynamic system into some partitions, and doing the partitions, if the variables do not change, change on making the partitions, dividing the system into partitions is called, those variables are called as intensive variables. So the variables intensive, okay, those variables, the variables do not change on making the system into partitions are called as the intensive variables. And the other variables, the variables which change on making the partitions in the system are called extensive variables. Okay, extensive variables. These are extensive variables which changes on dividing the system into partitions. For example, here I am taking some thermodynamic variables such as pressure, volume, temperature, internal energy, number of moles or amount of substance, amount of substance and density. Okay, let us take these variables, thermodynamic variables, as an example. So let us take a room or system. Consider this is the system. I am taking a living room here. Okay, so for this room, let us consider the pressure is nothing but the pressure is equal to 1 atmosphere, atmospheric pressure, and temperature is equal to room temperature of the surroundings is nothing but, let us consider 30 degrees Celsius, and volume is equal to, here the volume is equal to around 100 meter cube, 1000 meter cube, whatever it may be, just I am taking the examples. And internal energy, the energy, total kinetic energy possessed by all the molecules inside the room, nearly I am considering it around 200 joules. And amount of substance inside the gas, the number of moles I am taking it as 20 moles, amount of substance as 20 moles. And consider the density of the gas, we know it as 1.29 kg per meter cube. Okay, these are the things that are inside the room, right? Now I am dividing the system into partitions. When I divide the system exactly into half, this side pressure is again atmospheric pressure. So here another part of the room is also the pressure remains same. It is 1 atmosphere. So pressure and dividing the system into partitions, pressure is not changing. So pressure is a intensive property. I am writing I for intensive property. I am writing int in order to avoid confusion. Let us come to volume. So here initial volume is 100 meter cube. When I divide the system exactly into half, it will become 50 meter cube and this will become 50 meter cube. So the volume is changing. The variables which change and making the partitions in the system are called extensive variables. So here this volume is nothing but volume is a extensive variable. Now come to temperature. Here I am dividing the system. When you all of a suddenly built a wall in a room, the room temperature still 30 degrees Celsius here. In another part also the room temperature is 30 degrees Celsius. So on making the partitions for the system, the temperature is not changing. So the temperature is again intensive property. Right. Come to internal energy. So initially the total number of molecules inside the system are about 20 moles. Now when I divide the system exactly into half, the number of molecules this side around 10 moles and this side will be around 10 moles. So the number of moles are changing. So number of moles or amount of substance is nothing but it is changing, so it is extensive property. When number of moles changes, the amount of energy possessed by the molecules also will be changed. So this side it will be having 100 joules of energy and this part will be having 100 joules of energy. So here in this internal energy is also an extensive property because it is depending on the size of the system. When it is dividing into partitions, the internal energy is changing. So internal energy is a extensive property. So here when we are dividing the system into parts, the density of the gas this side, density is equal to 1.29 kg per meter cube, and this side is also density remains same. Density of a given material is same. Okay, so this side also the density is 1.29 kg per meter cube. We know that density of 1 liter water is 1000 kg per meter cube and density of 1 drop of water is also 1000 kg per meter cube. So there is no meaning of changing in density on dividing the system into partitions. So the density remains constant in this case. So the variables which do not change on making the system into partitions are called as intensive variables. So here density is a intensive variable. Density is a intensive variable. Right? So here these are nothing but pressure is intensive, temperature is intensive, density is intensive. They are independent of size of the system. Volume is dependent, internal energy is dependent, and amount of substance is also dependent. So these three are extensive property. Okay. Now first law of thermodynamics saying that the first law of thermodynamics. What is first law of thermodynamics? On giving the heat energy to the system, some part of the heat energy will be utilized to increase the internal energy, and remaining part of energy will be utilized to do work on the surroundings by the system. So we know dq is equal to delta q is equal to delta u plus delta w can be written as p delta v. So here this is extensive property. Heat energy supplied to the system is extensive property. Internal energy is also extensive property. So this also must be extensive property. This also must be extensive property. See here, the product of pressure is intensive property and volume is extensive property. The product of intensive property and extensive property is a extensive property. Okay, next. Now we are going to discuss about different thermodynamic processes. Thermodynamic processes. Okay, the first and basic process that we are going to discuss before going to discuss about all other processes are, first one is quasi-static process. Quasi-static process. We know static is nothing but at rest. When the state of a system is at rest, there is nothing changing. There is no change in pressure, no change in volume, no change in temperature, no change in heat energy supplied, no change in internal energy, etc. So the system should not be at stationary mode. So the system has to change its state from one to another, but it should not go through non-equilibrium states. So when the system is, we have discussed already in the previous section that when the system is going through non-equilibrium states, that is the expansion of gas against to vacuum, and another one is nothing but sudden explosion of chemical materials into small fragments, and also sudden explosion of cycle tube or sudden explosion of car tube is also an example of a system where it is going through non-equilibrium states. So in that case, we cannot measure the thermodynamic state variables. So the system has to go through equilibrium states. So in order to go through equilibrium states, the system is not to be sudden process or the system not to be at rest. The system has to go from one state to another state in very slow manner. That is nothing but quasi means semi static process. Semi static process. It should not be, the system should not be at rest, and as well as the system should not undergo sudden expansion or sudden compression. So it has to go from one state to another state in equilibrium mode. That is nothing but the process should be infinitely slow. Such infinitely slow process is called as a quasi-static process. We call it as quasi-static process. That means, so here I am taking a system like this. I am taking a system like this, and there is a movable piston. There is a movable piston, and consider there exist gas molecules inside the system. So here the system, we are not supplying any heat energy to the system here, and see here the system has to go from initial state P V T to final state P dash V dash and T dash. Okay, so in this case the system has to go through different large number of states. It has to go from P to P dash, suppose P to P1, P1 to P2, P2 to P3, and etc. And finally it has to go to P dash state. So it has to maintain the equilibrium state, that is mechanical equilibrium, that is final pressure. The pressure difference between final state and initial state is should be very less, and as well as it has to go through thermal equilibrium state. That means the final temperature and initial temperature difference should be very small. Such type of infinitely slow process is called as the quasi-static process or semi-static process. And all the thermodynamic processes that we are going to discuss about should be quasi-static process. Then only we can able to we can able to write the equation of state for different thermodynamic states, because we can apply thermodynamic variables only when the system is going through equilibrium states. So the process should be infinitesimally slow. Right. Now the another thermodynamic process is nothing but here isothermal process. Isothermal process. So in isothermal process, it is a thermodynamic process. TD means thermodynamic process, in which the system undergoes from one state to another state when temperature of the system kept at constant. Temperature remains constant. Here iso means remains same. Thermal, here thermal property is nothing but temperature. So temperature is constant in this process whenever it is going from one state to another state. So this is nothing but isothermal process of a thermodynamic system. So and second one is nothing but isobaric process. We know the bars are the units of pressure. So here isobaric is nothing but it is a thermodynamic process in which the system undergoes from one state to another state, when pressure keeping constant, when pressure remains constant. This process we call it as isobaric process. In isobaric process, pressure remains constant. And another process is nothing but the third process that we are going to discuss about, isochoric process. So in isochoric process, in this process, volume remains constant. And next one is adiabatic process. We know adiabatic walls are nothing but the insulating walls which do not allow the system to interact with surroundings. That means there is no exchange of mass and there is no exchange of heat energy between system and surroundings. So in adiabatic process, there is no exchange of heat energy between system and surroundings. In this process, adiabatic process, there is no exchange of heat energy between system and surroundings. There is no exchange of heat energy between system and surroundings. So heat energy remains constant in this process. So change in heat energy is equal to 0. Heat energy remains constant and change in heat energy is equal to 0. And change in heat energy is equal to 0 in this process. Okay. Thank you, students. This is the end of the class. And before going to end of the class, I'm going to I'm going to conclude the different processes here. For that I am drawing a table. Sorry, I'm going to draw a bigger one. Right. So here wait. Okay, so here on one side I am taking type of process and feature of the system. Okay, the first one is isothermal process. Isothermal process. What is constant here in isothermal process? Temperature remains constant. And next one is nothing but isobaric process. In isobaric process, what is bars are the units of pressure, so pressure remains constant here. Remember like this. And next one is nothing but isochoric process. In isochoric process, volume remains constant. And final one is nothing but adiabatic process. In adiabatic process, heat energy given to the system remains constant. So there is no exchange of heat energy between system and surroundings. This is the end of the class, students. Thank you. Have a nice day. Bye bye.